Hello everyone. So previously we had discussed on the topic matrix chain multiplication algorithm. So today we'll be discussing on the topic 01 knapsack problem, right? So this is one of the important this one algorithm. This is one of the famous DP this one algorithm, right? So let's see what the definition part say here. The 01 knapsack problem is a classic dynamic programming problem where we are given where we are given a set of items each with a weight and value. So where we are given a set of items, right? So each item will be given with this one weight and the value, right? Each this one item will be uh, this one will be having weight and value, or will be given with the weight and value, right? And a knapsack with a maximum weight capacity, and the maximum weight capacity will also be given, right? So what is our main goal here? The main goal is to maximize the total value of items placed in the knapsack without exceeding its weight, right? The goal is to maximize the total value of items placed in the knapsack without exceeding its weight. Each item can be either taken or left, right? 0 or 1. That is the reason we call this one as 01 knapsack. Basically each item can be either taken or left. This is, we can consider this one as 0 or 1, right? So let's move on with the explanation part here. So first thing, just listen to this carefully. We don't have to know everything in the theory. Just listen to this carefully. Whatever we discuss here, the same thing we'll be implementing in the form of code, or we'll be articulating in the form of code, right? So we have n items. We have n items, each with the value, this one value of I and weight of I. So we have number of items, n number of items, and each item will be having this one each items comes with a value of I and weight of I. This we know this from the definition itself. The knapsack can carry a maximum weight W, right? So the knapsack can carry a maximum weight W. The key idea is to decide for each item, this one. The key idea is to design for each item. So either we can include it or exclude it, including or excluding 0 or 1, right? So we will be making use of the dynamic programming to avoid recalculating the same sub problems. So that is the reason DP will be so handy, man. Yeah. So DP will be so handy sometimes. So but implementing the DP is big headache. So as I've said this one multiple times, you can just calculate this one. You can go with a graph. You can go with this one. What do we call arrays, strings, linked list, anything. It doesn't matter. But implementing DP, then the name itself states that it is dynamic, right? So the name itself states it is dynamic in nature, nothing but dynamic programming, right? So implementing it, so it will be different for different problems, and 1D DP, 2D DP. So this is fine if you understand the concept. If you know certain patterns, then it is fine. But it will be a big headache comparatively with the other data structures. DP is somewhat so you have to practice a bit. Rather, I would say, I want to put it in this way, that if you have to practice more rather than any this one data structures, you have to practice more the dynamic programming one. You never know what kind of questions will be asked in the interview, right? So if you go with a pattern, 10 patterns, you can be asked the 11th pattern that you have left, or you might not be knowing that pattern at all, right, in the interview. So that might also happen. Or you might be asked with something that you know, that might also happen. Yeah, that's fine. We can just try, right? So we can just try learning something new, and if we get a chance to implement somewhere, or if we get the same thing in the this one interview, we can just try to implement there, right? So that's what we can do. This is fine. Let's move on with the further things. We use dynamic programming to avoid recalculating the same sub problems. First thing here, we define a 2D DP table, right? So we'll be making use of the 2D DP, right? So this is fine. We define a 2D DP table, DP of I, W, where this one I represents the first I items. I, what it represents, I represents the first I items, and W, what W represents here, the current weight capacity. Yeah, where I represents the first I items and W represents the current weight capacity, right? So DP of IW, what it does, it stores the maximum value achievable with I items and weight W, right? It stores the total overall DP of IW, stores the maximum value achievable with I items and this one weight W. right? So the recurrence relation that we'll be going with here is just this one. See, you can just watch this one. Actually, we'll be making use of it within the code. The recurrence relation, basically the weight of the current item w, this one, weight of I minus 1 less than or equal to w, dp of iw is equivalent to the max of dp of I minus 1 w, value of I minus 1 plus dp of I minus 1 into w minus weight of I minus 1. So this is the recurrence relation we'll be going with. So next, otherwise, we'll be going with dp of iw is equivalent to the dp of I minus 1 w, right? So the same thing, let's try to implement the same thing in the form of algo or the code. So we'll be making use of the Python programming language, right? So let's go with the values or the profit of items. I'll just go with values here, that is equal to, I'll just consider the values 60 as well as 100. I'll just go with 120. Yep. Next, what I'll do, we have to consider the corresponding weights of items as well, along with the values, right? So algorithm states that actually it comes with the weights, values as well as the weights actually, right? So this will be 10, 20 as well as the 30, right? So this is fine. Now let's go with the maximum weight capacity of the knapsack. Nothing but W. Let me assign this one to the 50, right? Let me assign this one to the 50. Now let's go with the number of items, nothing but n equals length of, let me pass the values. Let me pass the values, right? So this is fine. Now let's initialize the DP table with the dimensions n plus 1 into w plus 1 filled with 0. So this one will be DP equals 0 uh, for, I'll just consider underscore. So this one in range. Hmm, let me go with w plus 1, man. Let me go with w plus 1 here. This is fine. W plus 1, also for this one in range, in range n plus 1. Yeah, this is fine, I believe. Now let's do one thing. Let's build the DP table in the bottom up manner, right? So I'll just go with a simple for loop here. So this one is for uh, I in range. So I'll just go with 1 comma n plus 1. This is fine. We are just going with a, we are just looping through the items in simple, this one in simple terms. Next, let's loop through all the possible capacities as well. So this one will be for w in range. Let me go with the range 1 comma w plus 1. Yep, this is also fine. The same thing we had discussed in the explanation, we are implementing in the form of code. Now, if the current item's weight is less than or equal to current capacity, then we have to take the maximum of the including or excluding the item, right? So accordingly with the explanation, else we cannot include the item at all. We have to take the value from the previous row. First, let's write the if condition. If current item's weight is less than or equal to current capacity. How can I write? If here we have considered weights, this is fine, weights of, I'll just go with the I minus 1. If it is less than or equal to W, then what we will do, let's take the maximum of including or excluding the item. So this one will be dp of I W. This is fine. Max of uh, dp of I minus 1. This is fine. Let me go with the W, right? So let me go with values of I minus 1. Let me go with the values I minus 1 plus dp of I minus 1, dp of I minus 1, w minus weights of I minus 1, right? So this one will be weights of I minus 1. Yep, this is fine. This is fine. Next, else what we need to do? Else, else what we need to do? We cannot include the item. We just have to take the value from the previous row. So this one will be dp of L W is equivalent to dp of I minus 1 and W. dp of I minus 1 and W. Right now, finally, what shall we do? Let's go with the maximum value achievable with the given weight. So let's print something for the this one. What do we call? Let's print something for the interactive purpose. I'll just go with the maximum value in the knapsack knapsack equals. let me pass the here this one dp of the solution will be present in dp of nw, right? Wait, the capital W that we have considered, this one. Yep. So this is it for the algo, right? So this is it for the algorithm actually. So what is the output? So we have the understanding, complete understanding of the algorithm, right? The same thing, whatever we have discussed in the explanation, we have uh, implemented in the form of code or articulated in the form of code. Now, uh, if we run the code, what is the output that we need to get here? Maximum value in the knapsack, maximum value in the knapsack, we have to get 220 here, right? So 220. Why we need to get the maximum value in the knapsack? So this one equals 220, right? So the output that we need to get here is 220. Why we need to get dp of 220? Sorry, 220 here. So first thing, let me explain you this one. Deep, we will be going with a dp of 0w and dp of I0. These both are zero basically with zero items or zero capacity. Initially, max value will be zero. Initially, max value is zero, right? So this is fine. For I equals one, for I equals one, this one for I in the range I comma n plus one. For I equals one, item one with a value 60 and weight 10. Item one with a value 60 and weight 10. This one, capacities is greater than or equal to 10. Capacity is greater than or equal to 10, right? So we are considering 10 in the weights. Capacity is greater than or equal to 10 actually. Yeah, so include it. So we will be including it. So dp of 110 equals 60 and dp of 150 is equals to 60 here. In this case, dp of 110 here equal to 60, and also dp of 150 is equivalent to 60 as well. Dp of 150 is equivalent to 60 as well. So this is fine as well. Yep. Now let's go with for I equals to 2. For I equals to 2. So let's consider here for I equals to 2. Right. So this is fine. When I equals, so when this one is for when I equals to 1. When I equals to 2, so item 2 with the value 100 and weight 20 we are considering. See, this one value 100 and weight 20. So we will combine item 1 plus item 2 at the capacity 50, right? So this gives actually 60 plus 100. 60 plus 100, this will be equivalent to 160. This will be equivalent to 160. Next, we'll be going with the third iteration when I equals to 3. When I equals to 3 actually, right? So item 3 with the value 120. So this one item 3 with a value 120 and the weight 30, right? So best combination at the capacity 50 is item 2 plus item 3, item 2 plus item 3. So when we sum up this one, so this one will be 100 plus 120. 100 plus 120 will lead to 220 actually. 100 plus 120 will lead to 220 actually. This is fine. So we have got the value 220. So the final maximum value for the knapsack capacity 50 is final maximum value for knapsack capacity 50 we have considered here. See, knapsack capacity 50 is nothing but the 220. 220 here we got 220, right? So this is the reason we need to get the output 220. Yeah. Now let's do one thing. Let me do one thing. Let me copy the entire file here. So I'll just give Control J. So this one clear screen, this is fine. Let me give Python followed by file name.py. So we have here line number 47. 47 else we are going with a dp of not lw man. So this one has to be dp of iw. Sorry. So let me give clear screen here. Yeah, now we are getting the output maximum value in the knapsack equals 220. So there was some typo here, you saw that. So this is fine. So now we are getting the desired output, right? So this is it for the algorithm. Simple one. Yeah, 01 knapsack problem. This is one of the this one actually one of the famous algorithms, right? DP algo basically famous problems or problem or the algorithm that you can consider. This is fine. Next, we will be going with a unbounded knapsack algorithm. So we'll be going with a unbounded knapsack algorithm. Yeah. Uh, now, this is it for the algo. Let me summarize whatever we have learned so far, right? And finish this off. So just give me a second here. The first point, I'll just Just try to remember these 4 to 5 points, man. So here, first point here is the 0, 1 knapsack problem helps us maximize the value. It helps us in maximizing the value without exceeding without exceeding weight limit without exceeding weight limit. Yeah, this is fine, I believe. Yeah. So the 0, 1 knapsack problem helps us maximize the value without exceeding the weight limit. So we will be making use of dynamic programming. We will be making use of the dynamic programming to avoid the recomputation. To avoid the recomputation by storing the results in 2D DP table. By storing the results in 2D DP table. Right. So the next step here would be the recurrence is dp of iw equals max of dp of I minus 1 w, value of I minus 1 plus dp of I minus 1 w minus weights of I minus 1, right? So when the weight permits, so this one we have seen in the this one, what do we call in the code, right? So this one, this part, yeah, line number 45 actually. This is fine. Overall, then let's come to the main part here. What will be the time complexity and the space complexity? Time complexity would be because of n into w, right? So and the space complexity would lead to this one. Let me write it here itself. Because n into w as well. The time complexity and the space complexity would lead to because of n into w. Right. So these are some of the important points I wanted to discuss with you guys. Right. So now we are done with a knapsack, 0, 1 knapsack problem or the algorithm, right? So next, as I've said, we'll be discussing on the topic unbounded knapsack algorithm. For now, this is it. Thanks for watching, guys.